For billions of years, a solitary world has circled the Earth, continuously counting out the months. The familiar features of the moon, so easily visible in the night sky, may seem unique. But across the solar system, another world, planet Mercury, bears a remarkable likeness to our celestial neighbor. Are these worlds truly alike? Could they, so far apart, share a common history? To answer such questions, we begin with the world closest to our own, an object whose regular cycle and supernatural glow have produced an endless source of speculation and wonder.
The two things that were most important to the ancients about the moon is that it moved through the sky rather quickly and that it changed. The fact that the moon changes its appearance so dramatically and so quickly is really the heart of what the moon meant to people. That meant really that the moon would be born, would grow, and would die, and then be reborn again in the course of a set of phases, or 29 and a half days, or 1 month. And that parable of the cycle of birth, growth, and death and rebirth is the real story of the moon in just about any moon mythology. It very often, but not always, was associated with a female goddess because, in part, of the connection with transformation, the female monthly cycle, and other aspects that relate to the overall concept of fertility. But there were male gods of the moon as well, and it would just depend on the culture and its way of life and its emphasis on the symbols that it saw in the sky that would determine what kind of god was climbing up there on the face of the moon.
In ancient times, people looked at the moon and they saw an object. They actually referred to it as a planet, an object that wanders across the sky. And they didn't think of it as a place. Even when Galileo built a telescope and looked at the moon, at first he didn't think of it as a place. But as people realized that Galileo was seeing mountains and valleys on the moon, they realized that if there's a mountain, you could climb it. If there's a valley, you could stand in it.
In time, people talked about other features. They looked at those great dark areas on the moon as if they were seas. In fact, the word for the Maria just means sea, even though today we know that that's not what it is at all, but this plain, hard rock. But as people kept improving telescopes, they did the very natural thing that you would do with a new world in space. They would map it, and they would keep mapping it in ever more detail, trying to see what kinds of features were on that surface, and of course, comparing them in their minds with the things that they knew best, those things on the Earth.
And then, as we began to understand what the moon was, and finally when we sent people there who actually did walk across the surface of the moon, we realized the moon is a place that we could go. And that means that now we look at the moon in a different way. Now it's not an object, it's a place.
If we go back to the days before the Apollo astronauts went to the moon, what did we know about the moon at that time? You could look at the moon with a telescope. We knew the moon was a body that was heavily cratered, many crater scars all over it, from asteroids falling in and hitting the moon. About 85% of the moon is bright, rough upland hills with craters just jam-packed, about as close as they can be packed. Then the other 15% or so of the moon are broad, dark plains of lava flows.
We now know those dark areas are lava, very much like the lava that it comes out of the bottom of the ocean, very much like the kind that makes the islands of Hawaii, that spread out over huge areas, thousands of miles in great plains. And that lava basins sit in an older surface. It's actually almost as old as the Earth itself, that's full of craters, that's very heavily bombarded, and which is a relic from, actually it's been dated about 4 billion years ago, when there was a very heavy episode of asteroid or cometary bombardment on the Earth as well, but this still survives from that period of time.
What we learn about that early period is there was very intense cratering for the first 500 million years or so. So many asteroids and leftover debris from planet formation were crashing out of the sky onto the planets. not only our planet, the moon, but also Mars and the satellites of Jupiter and Saturn and so on, all through the solar system. The moon actually gives us a record of that intense cratering.
Unlike the Earth, which also experienced this early cratering, the moon was not later reshaped through processes of erosion and large-scale plate tectonics.
As far as we know, there's never been running water on the moon or a very large atmosphere. For one reason, there's no evidence of erosion or evidence for lakes on the surface of the moon. There are things that look like they might be dry lake beds, but these are lava lake beds. The moon might have outgassed or degassed, as the expression goes, and gotten rid of all of its volatiles and put them into an atmosphere, but because the moon is so small and it has such a small gravity field, it was not able to keep this atmosphere.
If a planet is very small, that means it first of all doesn't have very much heat inside it, and second, it's easy for that heat to get out. It doesn't have to travel very far, and it can be radiated as heat into space, and the planet will cool off very quickly and stop being geologically active. The moon is like that. The moon is deader than a doornail, and it's been that way for 3 billion years.
Any planet that has not been very active geologically has an old surface, and any old surface is going to have been exposed and hit by passing asteroids and comets. Now, this actually gives us a tool to date, to get the age of the surfaces, because if you have a surface sitting out in the solar system and you get, nature is stamping out these little cookie cutter circles, one every 1,000 years, something like that, then you just count up the number of craters and you get a rough idea of how old that surface is. So scientists have begun using the craters as a way of establishing something about the history and the chronology of the solar system and the different planetary bodies.
While telescopic observations had taught us much about the lunar surface and its history, we had yet to see the far side of the moon.
The moon itself is asymmetric in shape, and it's been locked into position in orbiting around the Earth by the interaction of tidal effects on the Earth and the moon to lock it in always the same position.
If you watch the moon in the evening sky, it may seem that it doesn't rotate because we always see the same face of the moon. But the truth is the moon does rotate. It rotates on its axis once in the same amount of time it takes to go around the Earth. And consequently, it rotates to keep the same side facing the Earth at all times.
In 1959, the Soviet Union sent out a small spacecraft that did a giant job. It photographed the reverse hemisphere, the side of the moon that we never see from Earth itself. And we all expected when the pictures came back, it would look kind of like the front side. It doesn't. It's almost all white, old, battered terrain with only a few of these dark areas full of lava. And that was a real mystery. Why would one half of the moon be full of dark lava plains, the kind that we see from our side, and the other side without any at all? And the reason for that, we now know, is that the moon's crust is thicker on one side than the other. The moon has got a fairly thick crust. The whitish stuff we see is actually crustal, old crustal material. And it is not uniformly thick. And in the portions that are low, where great basins have been carved by giant asteroid impacts in the past, the lava from the inside has filled up. In areas that are high, the lava doesn't fill up. It can't reach it. It can't be pumped up high enough to flow out. And so the backside of the moon, from our point of view, is simply higher, topographically higher than the near side, which is filled.
By the 1960s, we knew a great deal about the moon solely from our observations. To gain first-hand knowledge, however, would require a new vision.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish.
That was a terribly exciting period for all of us. I was a graduate student during that period. There was a real sense of challenge in our department, our graduate program. I mean, you were part of this effort to go to the moon. We were going to land Americans on the moon, and I remember walking out of the building at 5 o'clock or 6 o'clock, and there was the moon up there, and it was going to go around maybe 30 more times, and we were going to try to fly somebody there, and it was just a sense of excitement.
Picking up some dust. More forward, drift into the right a little. Good. Okay. Contact light. Okay, engine stop. We copy you down, Eagle. Tranquility Base here. The Eagle has landed.
The Apollo program was, one of the justifications was, if we fly to the moon, we get rocks from the moon, we'll understand what it's really made out of, we'll get these very ancient rocks that are lying around in the oldest areas, and maybe they'll tell us how the moon formed in the first place.
The surface appears to be very, very fine-grained as you get close to it. It's almost like a powder. I'm going to step off the limb. It's one small step for man, one giant leap for mankind.
That's one small step for man, one giant leap for mankind.
When astronauts went to the moon, the first couple of landings were selected to be in very plain areas, very smooth, flat, uninteresting areas, because safety was the main concern. That, in fact, continued to some degree through all 6 of the flights to the moon. So we had 2 landings in lava plains. The other landings began to get a little bit more adventurous into some of the upland areas so we could sample different types of rocks. That way we learned a lot about the moon because we got the 6 different areas. At the same time, the Soviets, who we now know had tried to start a lunar landing program with their own cosmonauts and then given up because they realized they couldn't beat us to the moon, they took a different route. They built some automated ships and landed in 3 sites and scooped up some samples and brought back soil purely by automated sample return. So we have 9 sites on the moon. That characterizes the moon fairly well.
2, 1, 0. This will be having ignition. What a liftoff. And liftoff.
When astronauts began to bring samples back from the moon starting in 1969, and they were also able to put seismometers down, real seismometers with long-lived radioactive batteries to keep them going, at several different locations, so we could begin to look for moonquakes, which was the first direct way to find out what was happening inside the moon. The result of that is we know the moon is quite different on the inside than the Earth.
On the whole, the moon is made out of lighter materials. And in fact, the density of the moon is about similar to the density of rocks on the Earth or rocks in the mantle of the Earth. So, in a sense, we knew that the moon was made out of materials like the mantle or the crust of the Earth, but without the big iron core.
We think the moon is as though one took the mantle of the Earth and then refashioned it like a sculptor and made another smaller body out of the mantle with a little thin skin of crust. That's the white, lighter material that's so old and battered than the surface. We don't think it has the same things as the deep interior the Earth has.
So we knew there was a little bit of a problem. Why doesn't the moon have an iron core? And how do you make something out of similar material to the Earth but not get the iron that the Earth got? There were different theories about the moon before we went to the moon. None of them seemed to make sense.
First one was it was captured, that somehow the moon was a giant asteroid that, due to random collisions and so forth in the solar system, ended up getting captured by the Earth. That was one theory. A second was that the moon and the Earth were a double planet, and they actually formed together. You know, for some reason, we here got most of the mass, and the moon got a little bit, but really the same stuff.
Another theory was that it was spun off the Earth, but nobody could figure out how there could be enough energy to do that.
We know chemically, by analyzing the samples back from the moon, that they are really different from the Earth in a funny way. They're as though the mantle material of the Earth got heated up in a furnace. And so after all the Apollo program and all the samples back, we knew all about the history of the moon, but we still didn't know where it came from.
In the mid-70s, my colleague Don Davis and I were working on the problem of how the Earth itself accumulated from small bodies in the solar system, asteroid-like bodies which were colliding with each other and growing into planets. Some planets might escape collisions like this. Other planets might have catastrophic collisions. And we proposed that the answer to the existence of the moon was that one of these large secondary bodies crashed into the Earth and blew mantle material from the Earth, and of course from the mantle of the impacting body. All this mantle material went flying off into space around the Earth and formed a big cloud of debris around the Earth, which could have then condensed into the moon. Now, although that theory languished for a few years, and people said, oh, well, you're just dragging this thing out of the sky to make the Earth, and that sounds like a kind of a wild idea. It finally emerged. It was very exciting for us because after about 10 years, that theory emerged as what is now the leading theory on the origin of the moon.
If one simulates this on a computer, you could have an object the size of Mars around that collides with the Earth at the very end of the accumulation process. If that happens, objects that big, a jet of material can be shot out, melted, volatilized, and some of the elements lost in the process. And in fact, that's how we think the moon formed, that it was the result of jetting of material of a giant collision, cataclysmic collision, just at the end of the accumulation phase. The material then went out in first a disk, and finally into kind of rings, and finally accumulated into what is now the moon.
Countless years of cratering and cooling molded the familiar and seemingly unique satellite we see today. But nearest the sun orbits another celestial object with strikingly similar features.
To the ancients, the planet Mercury was connected with the god who was the messenger of the gods, a speedy god that moved back and forth, carrying this word and that word from one to another, the god of commerce as well. And the planet Mercury was a very speedy planet in the sky, hard to see because it's relatively faint, and it never moves very far from the sun.
When observed from the Earth with a telescope or a radar, it's never more than 28 degrees from the sun in the sky, so it's very hard to observe. You can imagine the scattered light that gets in the lens or the mirror in trying to look at it. So it's also fairly small. It's not much bigger than our moon. So the traditional ways of studying planets before the space age really didn't work very well for Mercury. We knew a few things about it. We knew that it was very dense because those few asteroids that move through the solar system on very eccentric orbits, when they got near Mercury, their orbit was changed a bit. So it meant that the Mercury was pulling it, and it was pulling it disproportionately for such a small object. Therefore, it must be a lot of mass, therefore it must be dense.
Astronomers believe that Mercury rotated with one face always facing the sun. In 1965, doing observations from Arecibo, radar astronomers observed that the rotation period of Mercury was 59 days. That's its day as compared to its year, which is its period of rotation around the sun of 88 days.
It's an object that has been most exposed to the highest level of solar-related processes of any object in the solar system. It's long since blown away its atmosphere, and so all it has is a most tenuous atmosphere that's caused through the interactions of solar particles with the materials that make up Mercury's surface.
We also knew that it reflected light just like the moon, and it reflected radar waves just like the moon. So it kind of said, gee, that's funny. It looks like it's dense. Maybe it's got an iron core. It's like the Earth on the inside, but it looks like the moon on the outside. What a paradox.
While early observations gave us basic information about Mercury, a single space mission revealed features both familiar and unexpected.
Well, Mariner 10, which is the only spacecraft to have gone there, was an elegant experiment launched by the United States in 1973, first to Venus, and it used a trick of a gravity swing by, a slingshot effect by the Venus gravity, to hurl it into Mercury, which is a very hard place to get to in terms of energy. And so Mariner 10 went by, and then in fact it was in orbit that it was able to make two more long looping passes around the solar system and then see it again. And what it discovered was it looks like the moon incredibly similarly in many ways.
They're heavily cratered, covered with impacts from when the solar system was young. One of the big differences is the moon has dark maria, great lava flows that flooded the lowlands on the moon 3 to 4 billion years ago. Those maria actually did form on Mercury, but chemical composition differences mean that the lava flows on Mercury are not as dark in color, and so they don't stand out. So in fact, Mercury and the moon are even more similar than they appear when we look at them.
If the surface of Mercury really looks like the surface of the moon, not just in little things, but in big things, have they had the same history as planets? And the answer is to some extent yes. That is, their external histories have been the same. The fact that the Mercury has very large basins that are filled with volcanic lava and also rougher, older surfaces around it means that they both saw that same episode of very heavy bombardment. And they're both recording that. That was an episode of bombardment that took place throughout the solar system, or at least the inner solar system. And it's our fundamental geologic yardstick. Our time scale comes from that. And that's how we relate the histories of these different bodies.
The principal difference is that even though Mercury's surface appears like the moon, Mercury is much, much denser than the moon. That means the core of Mercury is made up of something different than the core of the moon. Here, Mercury is an object about the size of the moon, but it has a density that's comparable to that of the Earth's density or the density of Venus. That makes Mercury a much different object than the moon for study, even though they appear physically the same.
In fact, there are scarps, there are other features on Mercury, when one looks more carefully, that are not like the moon at all. And those reflect the interaction of the interior, because the interior is totally different. It's got a huge iron core. It has to be 80% iron core and only 20% silicate mantle around it in order to make the densities work out. That was a big surprise. But there was an even bigger surprise, is that the same spacecraft had the ability to detect a magnetic field by looking at the way the solar wind, the plasma around Mercury, was perturbed. And to everybody's surprise, certainly mine, it has a small magnetic field, a dynamo inside. So it really is like the Earth on the inside, and it really is like the moon on the outside.
Since Mariner 10, scientists have continued to learn about the composition of Mercury's surface by observing the planet at a variety of wavelengths.
When we look at Mercury using all these different techniques like radio wavelengths, infrared wavelengths, optical wavelengths, we can really get a very good idea of what the upper couple of meters of Mercury's crust are made of. And to first approximation, Mercury really is very similar to the moon. Both objects have a very thick, what they call regolith layer, which is basically a dust layer, where the upper few centimeters is very fluffy, very porous, and the regolith below the first few centimeters is much more compacted.
Only optical pictures of roughly 40% of Mercury exist. Radar has imaged the entire planet. We were quite surprised in our initial observations of a bright patches on the north and the south poles.
It's recently been discovered that there's a polar cap on Mercury whose radar reflection properties suggest very strongly that it is in fact ice, H2O ice. So we're in a position here of having a planet that's very close to the sun. It's very hot over most of the surface, but apparently ice caps can form on the poles.
The orientation of its spin axis is perpendicular to the orbital plane of Mercury. So there are no seasons on Mercury. So the temperatures are very, very warm, 800 degrees absolute at the equator of Mercury, and yet you can have temperatures very well below freezing at the poles of Mercury.
So this has to be an accident of the way Mercury is tilted toward the sun. It can have shaded areas, and in particular in areas that are in permanent shade, you can expect to see solid ice. It was a surprise, however, to see such strongly reflecting polar caps from these radar measurements.
While Earthbound observations continue to teach us many things about Mercury, we have, in a sense, just scratched the surface.
We're looking at a study to perhaps orbit a spacecraft about Mercury. Sooner or later, we'll get a spacecraft in orbit about Mercury. It's just part of the natural evolution of human exploration. We haven't been there yet. I hope that soon we'll be able to get there and make us a long series of observations of a concentrated effort on this one very interesting and curious object.
Like each object in our solar system, the Moon and Mercury are unique. Their surfaces reveal a shared past, while their interiors suggest very different origins. As we learn more about these cratered worlds, we discover more about our world, our solar system, and its place in the infinite frontier.